Thanks all for joining us. This is Skype a Scientist Live. My name is Sarah McAnulty. I run the Skype a Scientist program. And today we are super lucky to be joined by Antonina Calahorrano-Di Patre. So thank you so much, Antonina, not Antonia, sorry, for joining us. Yeah, thank you for joining us. So would you like to, for everyone at home, we're going to be doing a brief introduction of Antonina, and then it's really all about what you're curious about. So if you have questions about volcanoes, what it's like to work in the field, what it's like to be a scientist, now's your chance to ask those questions. So you can submit them to the Q&A. Please put them in the Q&A and not the chat. If you have questions about Skype a Scientist, feel free to put them in the chat and I'll get to those as quickly as I can. But otherwise, the Q&A would be ideal. At this point, I'm going to hand it over to you, and then you can introduce yourself, say who you are, what you do, why you like it, and then we'll get into all of your questions at home.
Hi, can you hear me?
Sounds great.
Perfect. I'm going to share my screen.
Beautiful.
See. Haha. And there we go. Okay. So yeah, who am I? I'm a volcanologist. I'm actually still a student. I'm a PhD student. My job is to study volcanoes and what happens inside of them. My job is to find more about what is happening with volcanoes, something that no one else has known about them before. And in the future, I would hope to work forecasting volcanic eruptions and making the world safer for everyone. I specifically use gravity to study what's happening inside of volcanoes. I use a gravimeter, which is this instrument down here, with all the little knobs. And it's very interesting that we have a lot of ways to know what's happening inside of volcanoes, but still we need to complement all the different types of information that we get from these methods in order to try to forecast volcanic eruptions and also to know what happened in the past with previous volcanic eruptions. So, but what about gravity? It isn't like gravity constant on Earth, it isn't just a value, it's the thing that is keeping us like grounded, right? Well, we know that the gravity of a planet, for example, it depends on how massive it is. So for example, the gravity on Earth is higher, the value of gravity on Earth is higher than on the moon. And that's why we have all those videos of the astronauts on the moon just going really slowly and jumping, because their weight was less on the moon than on Earth. And that's because the Earth is much more massive, it has more mass than on the moon. That means that the value of gravity on Earth is not the same everywhere. So there's parts, for example, where there's massive mountains in the Andes or on the Himalayas, where you can see here that the value of the gravity is higher. So all the red spots is where gravity on Earth is a little bit higher, and the blue spots is where it's a little bit less. So, but by doing a map of how the gravity changes around the Earth, we can know what is happening below the surface. We can know if the rocks below the surface are more dense, for example, or we can know if there's, for example, gaps, there's holes below the ground, or there's, for example, underground water. But what does it have to do with volcanoes at the end, right? Well, volcanoes at the end, what are they? They are places where magma, which is molten rock, deep from inside the Earth, comes up because these rocks are lighter now that they are molten, and start to rise like oil in water, and then eventually they burst through the Earth towards the surface, and that is a volcano, just magma coming out of the surface of the Earth. When there is magma, new magma inside a volcano, it means that there's more mass. So now there's your volcano, and then there comes new magma from below, and now there's an object inside that there wasn't there before. So if we measure the gravity in this volcano before, and then after this happens, we're going to measure an increase in gravity. So we can know if there's more mass, so more material to cause a volcanic eruption in the future, if we measure gravity in time in volcanoes. We can also measure gravity in different spots in a volcano, around a volcano. And that way we can know, okay, in this spot, there's larger gravity, so maybe the rocks here are more dense. So maybe in the past, magma came through here and then it solidified. Or for example, we can measure and here the gravity is less. So maybe there's water inside this volcano. So maybe in the future, if there's an eruption, the hydrothermal system, which is how it's called when there's water stored in a volcano, this hydrothermal system might cause a different type of eruption that is caused by interaction of magma, which is hot, with water. So that's my job. I take my gravity meter, well, it's not mine, it's my university's, but I take it to different spots around the Earth, different volcanoes, and I use several ways of getting to them. Sometimes my favorite way is through helicopter travel. We get to different spots, we measure gravity, sometimes we go back so that we can measure if the gravity has changed in time. For example, here at Sierra Negra Caldera, we even got a little rainbow when we get there. We got there actually 2 weeks ago, so I'm just back from the Galapagos Islands. And that way we can monitor volcanoes, and we can also know what's the structure inside of them. But gravity is not the only way that we can monitor volcanoes. For example, here's a nice graph from the USGS with a lot of different methods, and I have a lot of colleagues that work on this. So you can do it by imaging, for example, with cameras. You can do it with remote sensing, which means that, for example, you can use satellite signals to see if a volcano has been deforming. So sometimes when there's more magma, the gravity increases, but also the volcano starts to inflate like a balloon, or deflate if there's less magma. So the ground of the volcano moves. Also, you can monitor volcanoes through earthquakes. So when the magma moves through a volcano, it causes small earthquakes. And if you monitor where these earthquakes are and how big they are, you can know how much magma, how is it moving, where it's located. So there's a lot of ways to monitor volcanoes. I used to work in the monitoring agency of my country, Ecuador. And yeah, I hope to continue doing that in the future. So I will take any questions now.
Awesome. Your job seems extremely cool. Any job that you take a helicopter to get to your study site is pretty cool. Could you stop sharing screen, because it makes Kay a little bigger, which is helpful for folks who really need to look at those hands. Okay, we've got lots of questions already, and I bet we're going to get a lot more. So thank you so much for sharing that. The first question comes from Natalie. Natalie would like to know what a volcano is made of.
What a volcano is made of? Okay, so the easiest answer is rock. It's always rock. Now, the question is, how hot is that rock? And how viscous, how melted it is. So it's basically, your rocks, consider your rocks like cheese. So if you increase the heat, then that cheese eventually, it depends on the type of cheese, right? Some cheese is more melty than other types of cheese, but eventually it will melt. So when you stop, when the cheese is not hot anymore, it comes back to a solid mass. Maybe it's not the same shape, but it's still going to be solid. So volcanoes are just rock, and rock, and sometimes a little bit of water. Especially, for example, if you think Mont Saint Helens, or another famous volcano, like for example, Mount Fuji in Japan. Those all have glaciers. So, for example, this one too. This is Cotopaxi volcano in Ecuador. A lot of volcanoes, because they are very high, they have a glacier cover, but most of them are rock in some state of melting. So a volcano with an active magmatic chamber, let's say, means that it has a certain amount of molten rock below the surface that has the potential to erupt at some point. And it depends on how much gas it has. So a volcano is basically rock, molten rock with some amount of gas inside. And how much gas it has inside means how explosive it will erupt and what's the potential of it to erupt in the future.
Sounds good. Thanks. The next question is from Jackson. Jackson would like to know, what do you think the next volcano to erupt would be? And like, how often are these eruptions happening? Like, is there a volcano erupting every day? How often is this happening?
Okay, so, and this is a very cool resource. You can go to the Global Volcanism Program. This is from the Smithsonian. And they have always a list of how many volcanoes are erupting around the world. And the list is usually about 50 volcanoes. So at some point around the Earth, at least 50 volcanoes that we know of are erupting. There are a lot of volcanoes that are under the ocean. So they are mid-ocean ridges. It's basically where the Earth is spreading and letting magma through. And a lot of them we don't know about. So for example, recently there was this big tsunami, you probably heard about it at Tonga. And that was from an eruption of an underwater volcano that we knew the location more or less because we know there's a spreading center there. But because we don't have a great way to monitor underwater volcanoes, we didn't exactly know the location. Monitoring them is a little bit more difficult, but at some point there's always at least 50 volcanoes that we know of, and many more below the ocean that are also erupting. When is the next one going to erupt? I personally don't know. I know that there's a lot of volcanoes erupting at this point. And also, it's if you have someone that tells you, yes, this volcano is going to erupt on the 10th of April at the midnight, don't believe them, because you cannot really predict when a volcano is going to erupt, but you can forecast like the weather. So you can say there's a chance that in 2 weeks, because we have seen an increase in earthquakes, for example, or because this volcano has been inflating, we know that the floor is going up, then this volcano has a chance to erupt in the future. And at this point, for example, we have a volcano in the Galapagos Islands called Fernandina, which is a little island. It's very nice that it's away from any population center. And this volcano, we know that there's been more earthquakes than normal. We know that the floor has been going up a little bit. So the Monitoring Institute of Ecuador has given a couple of reports saying, yes, we know that there's an increased activity in this volcano, and there's a chance that in the following weeks, I don't exactly know what's their scenarios that they have said, but there's a chance that in the following weeks, this volcano is going to erupt.
Very cool. All right, we have a couple people asking very similar questions all around the amount of time it takes for lava to cool once it comes out of the volcano.
Oof. Okay, so that depends on how hot it is, but usually you can go back to lava that has been erupted from volcanoes in the past after weeks, and it's still hot because when it comes out, it's really hot. It's more than 1000 degrees Celsius hot. Whoa. And it also, when it cools, when the surface cools, it kind of insulates itself. So maybe the surface is a little bit cooler, but then you measure the temperature with, for example, a thermometer. You try scraping at it with a hammer. That's something that they do at Hawaii because the volcanoes have an easier access. And suddenly there's molten lava below the surface, below this little crust. So it takes weeks to months to completely cool. And inside a volcano, because it's kind of isolated from everything, it takes months to years for new magma that maybe hasn't erupted, but we know it's inside of it, to completely cool. For example, Cotopaxi volcano, which is here again, it erupted in 2016. And my colleagues at the Geophysical Institute of Ecuador have continued to monitor with thermal cameras. They fly around, and then they point it at the crater. So for example, the temperature outside here, maybe it's like 30 degrees or something like that. But inside, because there's still gases coming out from the continuous activity of Cotopaxi, it's very, very hot. It's more than 100 degrees hot. So yeah, it depends on the volcano, of course, but if lava has erupted, it needs a lot of time to cool.
Cool, sounds good. A couple questions how are you staying safe when you're studying volcanoes and getting close to volcanoes?
Okay, so this again depends on what you're doing. So because I do gravity and I do in general geophysics, so I study the physics of volcanic eruptions, I usually deal with instruments that do not need to be around the volcano exactly as it is erupting. So usually what we do when working in an active volcano or a potentially active volcano is we have the help of our colleagues at the monitoring institutes that tell us, okay, this morning we have this amount of earthquakes in the volcano. The deformation is blah, blah, blah. We know that with the way that we monitor the gas coming out of the volcano, that there's this amount of volcanic gases coming out of it. So we don't think that there's any particular danger in the following hours of you going there. But we always have maybe a satellite phone or maybe a radio. We have some way of contacting them so that if they see any change in the internal activity of the volcano, they say, okay, you have to get out of there.
Right, right.
Of course, it depends on if, for example, right now, Sierra Negra, the volcano in the Galapagos that we were working 2 weeks ago, its activity is pretty normal. An active volcano always does something, has some activity inside, but it's not enhanced activity. So we're not expecting the following weeks an eruption. So we didn't have to every day call them and say, hey, did you see any changes during the night? But for example, there's other scientists that have to work while the volcano is erupting. So some of my colleagues had to go there and sample the fresh lava from the volcano. In that case, they need to be first of all, they always have to have some sort of escape route, be it with a helicopter, be it that they know they have like a path that they know the lava or whatever volcanic product is not going to get to. They have to have an escape route. They have to be very vigilant about any changes in activity, again, with the help of colleagues in the ground, looking at the signals inside the volcano. And of course, they need to trust their own judgment and be very, very safe. If something is maybe a little bit too long to get to, sometimes it's not even something about being too close or anything like that. But if for some reason they could take 2 more hours to get to a certain spot by walking, and they do not have that kind of time before it gets dark, at that point you decide, well, you just cannot do the work.
Yeah, sounds good. Can you outrun a volcano?
Depends on what the volcanic, I'm going to say depends.
A lot of depends, yeah.
But yeah, okay, so it depends on what the volcano is doing. For example, again, with the Galapagos Islands or Hawaii, the Hawaii volcanoes, lava flows, depending on how they get out, they tend to be slower. So, for example, you can, if they go 10 meters per second, something like that, you can outrun a lava flow. But there are a lot of volcanic products that you cannot outrun. For example, in explosive volcanoes, for example, the ones in Japan, the ones here in Ecuador in the Andes Mountains, the ones in the Cascade in Oregon, for example, Mount St. Helens is one of the examples. They usually do not erupt in an effusive manner. This means that if they don't, their products are not lava flows. They are things, they are more explosive. So they tend to be these really, really fast clouds of hot gas and volcanic products and rock. They are basically landslides of really, really hot vapor and rock. And they go faster than any even car that you can think, like 150 kilometers per hour, something like that. These things you cannot outrun. And that's why for most of these volcanoes, you have what these are called hazard maps, in which the areas where these volcanic products are probably going to be in place. So where the scientists, because of previous eruptions and because of other things regarding how big the eruption they think is going to be, they say, okay, the pyroclastic flow, that's how these landslides of hot rock, really fast hot rock are called, they are going to stay in between this border with a certain error. So please, if there's an eruption going to happen soon, don't stay there. So that's something that, for example, in Indonesia, they have very clear. And so there are zones like red zone, yellow zone, green zone. where in case of an eruption, you absolutely cannot stay here. In case of an eruption in the yellow zone, maybe you can stay until there's an alert, something like that. Other products of explosive volcanoes, like the ones in the Cascades, are lahars. So lahars are basically very fast mud flows.
Oh.
And that's because if you have volcanoes that have a glacier cover, and then the volcano erupts, all this glacier just melts. And the problem with lahars is not just water, it's kind of because the water mixes with the volcanic ash, it starts carrying really big rocks. It's basically, it's a river of concrete with big rocks, and it starts building into itself. So the farther it goes, actually, the stronger it gets. Again, we have the hazard maps to say, okay, through this river channel, there's going to probably be a lahar, so don't stay around this area.
Right.
Again, you cannot outrun this kind of really, really fast mud flows. Ash, volcanic ash, because it's erupted into the air and then it spreads with the wind. In that sense, it's basically like rainbows of ash. You cannot outrun it. And in that sense, you need to be prepared to deal with it. Masks, for example, are a staple in my country. When I was very little, instead of snow days, we had ash days when there was a volcanic eruption and the school was canceled because there was ash everywhere.
Right.
Volcanic ash, because it's really fine rock pulverized, and it's also a glass type of rock. If you breathe it in, it's very dangerous for your lungs. It's basically like breathing little particles of glass.
Wow.
You have to cover your eyes, you have to cover your mouth, don't be outside. It's a problem for farmers because their animals are outside, they have to deal with it, they don't have food because it covers the grass that the animals eat. And also because it can accumulate like snow, but it's very heavy because it's basically pulverized rock. It can collapse buildings, it can collapse roofs. So you have to plan on cleaning it every time. And it's something that usually you have to deal with long time if it's a prolonged eruption. And governments usually have some sort of plan to help people.
Very cool. Michael from Mrs. Weaver's class in Morrisville, North Carolina, when you were talking about those like big plumes of gas that you can't outrun, what is the gas in there that's dangerous?
It's not so much that the gas itself, well, it's dangerous. The gas itself is dangerous, but the problem is that it's very, 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 very hot. Oh. So it's like, it's so hot that if you breathe it in, it basically would boil you from the inside, which is a very, very grim prospect. I'm sorry. It's basically what happened to the poor people at Pompeii. So maybe you have heard of this whole town in Italy, Roman town that was wiped out by Vesuvius, because Vesuvius is also an explosive volcano. There were these gigantic pyroclastic flows that basically covered the whole town. And the people, yeah, they were buried because this plume is not only gas, it's gas with pulverized rock and volcanic products inside. The town itself was buried. The archaeologists had to basically bury down to find the poor people that were trapped inside. But the people died because of the heat. The thing that really, really kills you is the heat. Of course, inside there's the main products of a volcanic eruption that, well, actually the main product of volcanic eruption is usually water vapor, but that's not something that we usually think about too much because we cannot monitor it. Water vapor is all around us. But the volcanic, specifically volcanic gases, they have always something to do with sulfur, for example, sometimes even chlorhydric acid, stuff like that. But it's usually some sort of product of sulfur that always, it's a little bit acidic, it interacts with your lungs. It's not great to breathe. But in this case specifically, the thing that kills you is the heat.
Sounds good. Thank you for that answer. We've got a third grade class that has a bunch of questions. Mr. Legama's class. How does the lava get inside the volcano in the first place?
Ooh, okay. So here's a complex answer. So we know that in the inside of the Earth is very, very hot. And this is a remnant from when our Earth was created. So the internal heat of the Earth is a residual of all this friction from when it was created and also from radiation. So there's elements inside that are still decaying, and that means that there are some elements that are converting into other elements. But when they are doing that, they are also expelling a lot of heat. So that keeps the inside of our Earth really warm. There are several processes in the surface of our Earth that are causing this heat to be able to go up, basically. So maybe I will share my screen really quickly to see if I have, there we go, a photo to share this. So we know that our Earth is like a little puzzle. So those are the plate tectonics. So there are parts of the surface of our Earth that are all fitting together, but moving because below the Earth, there's the mantle, which is kind of, it's not exactly completely liquid, but it's molten, it's very fluid. So it moves around, and it makes that the plate tectonics move around too. So there's parts in the surface of our Earth that are spreading. So they are breaking and allowing part of the mantle to go up because it's lighter. And when you crack basically the Earth a little bit, the mantle comes up and outside. Now, because there's also this movement of plate tectonics, there's parts of the mantle that come out in the spreading center, but then they are carried inside another plate. So there's plates that are a little bit denser than the other, and they start, when they encounter each other, one of them starts to go inside the other. And that's what's called subduction. So you have the spreading center where you have the volcanoes usually under the ocean. And then you have the volcanoes caused by the subduction, which is when one of the plates is coming inside the other and then carrying water inside and making the melting point. So the temperature at which the rocks are allowed to melt a little bit lower. So you suddenly have volcanoes just in the boundary between these two plates. I'm going to stop sharing so that your hands can be seen. Okay, so basically there are different ways in which magma can come up. Some of them it's because you are basically cracking open the Earth, and then the magma is like, oh yeah, I have a place to go out, and boom, and goes out. That's the spreading center. Then you have the subduction, where you are basically lowering the temperature at which the rocks can melt. And that's, for example, the Cascades, the Andes. And then you have a third option where they are called hotspots. And they are basically, we actually have a lot of theories about hotspots. The more accepted right now is places where basically the overlying crust, the surface, it's a little bit thinner. So that means that the mantle can come up more easily. And that those are points, for example, Hawaii is a hotspot. The Galapagos Islands are a hotspot. And there you have, basically, it's very funny because you have the hotspot that is in the same place, but because the plates are moving always to one of the sides, then you have these islands that are in a little line, and the islands that are to the side where the plate is moving are older, and the islands that are just on top of the hotspot are younger, and they are literally islands caused just because of volcanic activity.
Awesome. Thanks. That's super helpful. We've got a question from Mr. Soskill's 5th grade class. If I wanted to become a volcanologist, what would I need to study? What kind of education would I need after high school?
Oh my God, I love this question. Thank you so much. And I love this question because there's no right answer. For example, I myself, I studied physics in my undergrad. So when I graduated from high school, I just knew that I liked science. I actually also played the violin. So I did a year of violin before that, and then I realized, no, I want to do science. And the science that for me was kind of the more rounded, the one that encompassed everything, was physics. So I graduated from physics, and I actually was thinking of doing cosmology, of studying the cosmos, how the big forces of the universe work. But then I did a little internship in the monitoring institute of my country, and I realized that I really liked volcanoes. First of all, I really like to see the physics kind of in action in this type of setting. So I then did a master in earth sciences after I did physics. So I basically am a geophysicist much more than a volcanologist, but I do the physics of volcanoes, so that's why I mostly say I'm a volcanologist. But you can also start by doing earth sciences from the start. So basically by studying geology and then going into whatever specialty you like the most about the earth, in this case, volcanoes. For example, in the group where I work, my lab mates, the people I work with, some of them actually do mostly the chemistry of volcanic eruptions. Some of them do the tectonics, so basically what is the Earth, the big forces from the plates that impact volcanic eruptions. My boyfriend, actually, who is also kind of a volcanologist, a geophysicist, he did physics and then he did maths. And then he applied all these sciences and mathematics to volcanic eruptions. So basically, you can study sciences and then get into volcanology, or you can start thinking about going into volcanoes and do earth sciences and getting into volcanology. But because there are so many things that go into volcanic eruptions, chemistry, physics, math, you can basically come from almost any science, maybe not biology, but there's also people that do biology in volcanoes, so that's very, very cool. You can come from almost any science, and yeah.
Ecosystems that take over after a volcano happens. That's biology. It's not actively volcanology, but it's adjacent for sure.
Yeah.
Very cool. So we have a lot of questions that are basically asking, like, how so we know that there's magma under the crust, and there are some spots and situations where the magma comes up and then you have a volcano. But how, like, what makes it kaboom? Like, what makes the eruption happen?
Okay, so the short answer is gas. And it's almost always going to be gas.
Okay.
So basically, the magma itself has a certain amount of gas inside because there's a lot of stuff happening in that magma. Now, it depends on the composition of the magma, depending on how much gas it stores inside. So, for example, we have a whole lot of volcanologists working on this, on how not only the gas, but also how viscous, how thick, how sticky the magma and then the lava that comes out of the volcanoes is. So the more viscous the magma is, the more it traps the gas inside. So it means that the gas, when it starts to come up, so when the pressure from above, so you have a lot of rock above it, and then suddenly magma starts to come up because of the gas. So the more it comes up, the more the pressure, there's less pressure, and the more the gas wants to come out. So this is basically like a Coca-Cola bottle. So if you screw it shut and then you shake it, then all that gas wants to come out. If you open it, it's going to go like boom. And it's the same with volcanoes. So either you have a lot of gas that at some point wins and gets the magma to come out, or for some reason the volcano gets open somehow. That's what happened with Mount St. Helens when there was that big deformation, and then one of the flags completely basically collapsed. That basically unscrewed the Coca-Cola bottle, and the whole thing went boom. So volcanoes in the Cascades, for example, volcanoes in subduction zones, they have a lot more gas content. They are also more viscous, so the gas gets trapped for longer inside. Mm-hmm. So the eruptions are much more violent because when the gas reaches that point where it comes out really violently, really explosively. So they are explosive eruptions. Volcanoes in Hawaii, in the Galapagos Islands, we call them basaltic volcanoes. The content of gas is lower, but the viscosity is also lower. So the magma is much more fluid. It allows the gas to escape easily. And that means that the gas carries the magma out, and it allows it to the eruptions are effused. So the magma comes out as lava, sometimes as these nice fire fountains, we call them. So this spatter of lava that then accumulates, and then it starts with those lava flows. But that's why there's a big difference between basaltic volcanoes, where there's a higher chance of effusive eruptions, and explosive volcanoes in subduction zones, where you have pyroclastic flows because just the whole thing just goes boom. But the answer is always gas.
Gas is the answer. Gas and the type of situation you have under the earth. Very cool. So this question is slightly related. It's from Miss Nielsen's Earth Science class. So is the hole on the top of the volcano basically just the result of the top flying off, like the explosion happens, and then that's how you get the hole at the top?
Well, it depends again. So in volcanoes that are, if you think about the really pointy ones, stratovolcanoes, they usually have one crater in the center. That's usually the preferred way of the materials to go out. So they have a preferred conduit, and that's basically where you usually get the eruptions. Now, in the case of, for example, Hawaii volcanoes, it's much more common to have fissures. So basically the earth cracks open, and then from there comes all the material. And then because of the accumulation of material, you get a little cone, as we call that a spatter cone, a cone that is like a mini volcano. So you get these really huge shield volcanoes, they are called, because they are an accumulation of all this material that has come out slowly. So they are usually like shields, like downtown shields. And then around them, you have little splinter satellite cones, little volcanoes all around, where there have been fissures in the past and the material have accumulated in a cone. Stratovolcanoes are basically these cones in big, because they accumulate a lot of material, ash, pyroclastic flows, bombs in one volcano that has done a lot of eruptions throughout its history. Then you have a volcano that is basically an accumulation of all these materials with a preferred opening. But these volcanoes usually in our lifetime, maybe not so much, but in their geologic history, which is really, really big, really long, they get destroyed and reconstituted so many times. So for example, Cotopaxi, now I think it's Cotopaxi 4 or something like that. So after big eruptions, the whole thing comes down, and then the process starts again. Sometimes, for example, if you think about calderas, you have a very big hole. So basically you have the shield or like an area, and then a crater that is gigantic, the whole thing going down. So in that case, it's not that the whole thing erupted, but rather that because the magmatic chamber inside got depleted, for example, the whole floor just went down, collapsed, which is what happens with the Sierra Negra. Maybe I can show you the picture. Because it's so big, I cannot show you the whole thing, but that's what a caldera is basically. So this is like 9 kilometers across, and you can walk all around it. And this is where basically the size of this hole is more or less the size of the magmatic chamber below. And at some point there was a bigger option where the whole thing collapsed down, but it's not like this whole thing just was erupting, like in the case of Cotopaxi, when you can see the material coming out of the one hole, the crater.
Very cool. Very cool. So we have a bunch of questions that are asking, like, how does a volcano become dormant, and how do people know that it's dormant, and are sometimes people wrong that they're dormant and then they end up exploding?
Okay, so this is the question that plagues volcanologists all around the world, and the question that we aim to answer once and once again.
Right.
So here we need to be very clear about definitions. So you have extinct,
okay,
active, potentially active and dormant. So in the case of extinct, we usually talk about volcanoes that haven't erupted in a long time, not only in comparison to our lives, but to their geologic history. So volcanologists, what they do is go to volcanoes. We know that they are volcanoes because the type of rock that comes out of it is very distinct. They map these rocks. They do take these rocks and then they try to know how old they are. So if they don't find evidence for younger eruptions, let's say 20,000 years, it's even more sometimes, depending on the volcano, they say, okay, this volcano probably with a very high probability does not have an active magmatic system anymore, is extinct. They also can do, for example, mapping of what's inside the volcano. So for example, what I do with gravity, earthquakes, when they travel through the volcano, there's something that is molten, they travel a little bit slower. So we can know in that sense if there's magma below that is molten. And they say, okay, it seems that the system inside is not really active, so this volcano is extinct. We think that it's never again going to erupt. Then you have potentially active, which is volcanoes that we know that in the closer geologic history have had eruptions. And that means that there is a chance that they become active in the future. We don't have evidence that they are active right now. So for example, there's not gases coming out of them, or the eruption, the last eruption that they had has been far away, at least for us, for our history as humans, but they can become active again. So these volcanoes, depending on how close they are to populations, on how do we think they might impact, or how close the last eruption was, you can either monitor them, so maybe put a seismometer to see if there's earthquakes on them. But usually they are volcanoes that are a minor concern, but you want to still look at them, see if there's any chance you start monitoring them again. Then you have active volcanoes that are not erupting right now, but that they might erupt in the near future. So volcanoes that have earthquakes happening all the time. Active volcanoes are always doing something inside. It means that there's an active magmatic system. And then volcanoes that are erupting right now. So it means that there's gases, volcanic products coming out of them all the time. It means that there's either lava or pyroclastic flows or ash. Those are active, those are erupting. But active volcanoes that are not currently erupting, those are dormant. And dormant volcanoes that we know they are active need to be monitored in order to give heads up to the population.
Sounds good. Thank you. So we are almost out of time here. We've had a couple questions. Let's try to answer this one as quickly as possible so we can ask you our final two questions that we ask everybody. Like if I look at a mountain, like does that have the potential to become a volcano, or are some mountains just mountains?
There are mountains that are just mountains, and usually you will know that because of how they have been created. So for example, I think about the Himalayas that are very high, but they are not volcanoes because they don't have any type of magma coming from below, because they are the product of two plates that have crashed, but they are the same density, so they just did this basically. There are mountains even in subduction zones, for example, where we know that the whole thing is the product of subduction. Usually, you know that a volcano is a volcano because the thing that is made of is volcanic rocks. Now, there's cases in which suddenly from places where there has been nothing, there's a volcano after a bit. So that's the case of what happened, for example, at Paricutin in Mexico. In a farmer's land, actually, suddenly he started to see that there were cracks in the ground and hot gases coming from them. I think Paricutin was caused by a little hotspot again. And these type of things are very difficult to monitor and to know when they are going to happen or how they are going to happen. but usually you will have some sort of evidence that a volcano is a volcano with gases or earthquakes or, for example, deformation. Usually active volcanoes, they do something, and mountains that are not volcanoes, either they don't have the evidence of previous eruptions. So for example, layers of ash around them, volcanic products, rocks that have been the product of volcanic eruptions. Or they are very, very quiet in the sense of geophysically, they don't have earthquakes, they don't deform, there are no gases coming out of them.
Yeah. Awesome. Thanks. This has been so informative. I just learned so much. I love running this program because I get to learn about all sorts of things like once a week. It's the best. So thank you so much for sharing everything with us. This was really amazing. And thank you everybody at home for asking all your questions. We got to 53 questions, which is a lot, but there were 115 more. So if you would like to talk to a volcanologist, you can always request your own on skypeascientist.com and have just your class talk to a volcanologist or a bird biologist or a plant scientist or a glacier scientist or whatever. So if your class is just so curious and full of questions, you can always request somebody just for your class. We always like to end these sessions with the same 2 questions. And here they are. The first question is, if you had everyone's attention in the whole world and you could tell them one thing about your area of expertise, what would it be?
Okay, this is not specific about my area, but it's about hazards. And my one thing is have an emergency backpack, have an emergency plan, because not only for volcanic eruptions, which is the thing that I care the most about, but about so many different natural hazards. And wherever you are, there's probably some sort of natural hazard that affects you. You need an emergency backpack, you need an emergency plan, because you never know when something is going to happen. Being prepared means that not only you are going to be safer, but you can also help your community.
That's a great answer. Very, very helpful, useful information. All right, the second question is, you still have everybody's attention in the whole world and you can tell them something about anything. It can be as silly and insignificant, like my favorite book is this, or it can be big picture important, like at the level of carry a go bag or have a go bag in your car or whatever.
I think the favorite thing that I learned when I started studying volcanoes is that volcanoes deform, like the ground moves when there's a volcanic eruption, but sometimes they do it in a crazy, crazy way. Sierra Negra, the one that we have been studying, the floor of the caldera moves up so much before an eruption. Before the last eruption, it was moving 18 centimeters per month. So between 2 eruptions, between 2005 and 2018, the floor rose up like 6 meters. So that's a whole room. And the whole thing was moving up. And it's crazy. It's just because there's more magma coming in, there's more gas. And the thing that you can basically almost maybe not see with your own eyes, but you can see the effects of this long-term in volcanoes, that they go like, for me, it's amazing. It's super crazy.
That's awesome. That's super cool. Well, thank you so much for all that you shared with us today. Is there anything else you'd like to mention, to plug, anywhere we can follow you on social media or whatever?
Well, I have a Twitter, Antonina CDP. I haven't been as active as I would like, but I usually post cool things about volcanoes there.
Very cool.
I would like to just say that geology, earth sciences is not only about oil or mining. There's a lot of other things that you do, for example, glaciology, volcanology, monitor earthquakes. There's so many things that you can do in earth sciences that are usually frowned upon because of oil and mining industry. That yeah, I would like more people to know even that they are cool, basically.
Right. Sounds good. All right, thank you again. Everybody, next week on Tuesday, we just super last minute are putting together a documentary screening on World Water Day, which is on Tuesday, March 22nd. We're going to be screening a 40-minute documentary on glaciers called The Last Glacier. And then we're going to have a glaciologist, so a scientist who studies glaciers, and the filmmaker to do a little Q&A after. The Q&A will be shorter than our normal Q&As. It'll be like 15 minutes instead of 45, but it should be really cool, and it's free, just like everything else we host. You can watch with your class and then join in the Q&A. So I posted the link there. It'll be up on our website shortly. This has been, anyway, it's happening. We just got contacted by the documentary crew yesterday about doing it. So we're putting it together a little last minute, but it's going to be great. So we're really excited. That's all I have to say. Thank you so much all for coming. This will be posted on YouTube after, if you want to rewatch anything or share it with anybody. Antonina, again, thank you so much for all of this.
Thank you so much for having me, really. This has been a blast.
Awesome, thanks. And thank you, Kay, as well, for interpreting. We always appreciate you. All right, we'll see everybody next week. Bye.